My name is Adi Afam bin Adnan. My metric number is 230553.
Assalamualaikum. My name is Sarah Yasmin binti Muhammad. My matrix number is 231015.
Hello, my name is Nur Alia Arisa binti Zulkifli. I am from Group 3 and my metric number is 230635.
First experiment, we aim to study the characteristics of the image formed by convex lens under the different object position. By constructing an optical setup, we will analyze the lens form a sharp, inverted image of an eye object. The result will be compared to a theoretical prediction based on the lens formula. Where f is the focal length of the lens, v is the image distance, and u is the object distance. This experiment helps depends of the understanding of the principle of refraction and the properties of lenses. In the second experiment, we use a spherometer, which is a precision instrument based on the micrometer screw principle. This spherometer helps in determining the radius of curvature of a spherical surface. The instrument works by measuring the height difference between the center edges of a spherical object. Using this measurement, the radius of curvature can be calculated. Additionally, the radius curvature of the convex lens can be measured using a spherometer that has three adjustable lengths arranged in a triangular shape. This mechanism enables precise measurement of a small height difference, which are essentially for calculating the curvature of the surface. The three legs of placed on the surface and the central probe is lowered until it touches the center of the spherical surface. The height difference between the probe and the legs is then measured. The process includes placing the spherometer on both the convex lens and the plane mirror, counting the screw rotation, and calculating the pinch and least count to accurately determine the radius of curvature. The relation between the radius and the focal length can be seen in this equation.
I would like to explain furthermore about the result from this experiment. As we can see, we use two different convex lens with the focal length of 100 mm. From the table 1, the data of the distance object and image form is increasing. After getting all of the data of object distance u, image distance v, and focal length f, we should find the mean of all those things to get a lens formula verification. By averaging object distance u and image distance v, you can test whether it satisfies the lens formula or not, which is 1 over f equals to 1 over v plus 1 over u. The mean value provides a better estimate on how well the lens formula works over a range object placement. Then, the focal length is a fixed property of the lens, so ideally, the mean focal length should match the actual focal length of the lens. If not, this indicates experiment all errors. For the table 2, the means of all data are increasing due to increasing distance of object and image. The individual focal length f equals to 10 cm is slightly different from the average of individual focal length 10.4 cm. The individual focal length f approximately 10 cm is slightly different from the average of individual focal length 10.4 cm. The small discrepancy may arise from rounding errors or variation in measurement. The result shows how using mean values help verify the consistency of the lens formula. Now, let's look at the table 3 that determines the radius of curvature of a spherical surface such as length of mirror. The result shows the circle scale reading, number of complete on plane mirror surface, number of discrete scale division in rotation, incomplete rotation, and total reading. As we can see, the data is precise. That means that it shows the distance between the legs of the base radius of the circle arc. By measuring height difference h between a flat reference surface and the spherical surface, we have find the curvature. In short, the smaller the radius of curvature r, the stronger the curvature length and getting the sharper focus. The larger the radius of curvature R, the weaker the curvature length and the focus is broader.
Hi, Assalamualaikum. So for my part, I'll be presenting about the discussion of the experiment, which is experiment 9, image formation of a convex lens. For table 1 and 2, we want to find out the focal length of the convex lens by using calculation. Alternatively, we can also get the focal length without using calculation by shining a light through the convex lens, and then we will adjust the distance of the lens until the image is sharp. Basically, the light is coming from infinity. Then, we will measure the distance between the image and the convex lens to get a rough estimate for the focal length. This is because the clear image can only be formed when the light is focused at the focal point of the lens. Either way, for this experiment, we want to find the focal length of the convex lens using calculation by getting the distance of the object and the image. The distance of the object from the convex lens will be our u, which will be our manipulated variable since we want to find multiple measurements to decrease the error for this experiment. Then, distance of an image from the lens, which will be our v, will be our responding variable. Hence, our fixed variable for table 1 and table 2 will be the same type of lens, meaning that it will be the same convex lens with the same focal length, which is 100 mm. From this experiment, we can get the object distance and the image distance, and from these two results, we can find the focal length by using the focal length equation, and then we get the average for each result. In table 1, for object distance, which is our u, we can get the mean of the result of 15.92 cm, and for the image distance, which is our v, we can find the mean of the result is 39.08, while the mean focal length that we got from our calculation is 10.23 cm. Meanwhile, for table 2, for object distance, we can find the mean of 16.4 cm, and for the image distance, we can get the mean of 28.6 cm. And for the focal length, we got a mean of 10.4 cm. To conclude, for these two tables, we can say that the length of the convex lens are 10.32, since it's the average from the table 1 and table 2, which is close to the actual focal length of the convex lens. Hence, the percentage error for this experiment is 4%. For table 3, we just want to find the radius of the curvature of the convex lens, R, by using the spherometer. The data we obtained from the experiment is we got the value of R 7.19 mm after the calculations. Since the value of R is positive, it shows that it's a convex lens. Since the radius of a convex lens is always a positive value. Meanwhile, for the concave lens, the value of R will always be negative. So, in conclusion, for this experiment, we can figure out the basic concept, including the behavior of light rays when it's refracted. The convex lens focal length will always be positive value, and apart from that, these findings emphasize the foundation law of optics and the application in fields such as imaging, communication, and optical instrument. This experiment has deepened our understanding of light predictability behavior in various contexts. That wraps up our presentation about the image formation of a convex lens experiment 9. Thank you so much for watching, and goodbye.